Well, how we're going to run this session is that we're going to have a tag team presentation here from Jay Richards and Guillermo Gonzalez. So they'll be switching back and forth as they introduce to us their book, The Privileged Planet. This just got released a few days ago. It's an excellent book. We've already been selling it at Reasons to Believe, packaging it with our Origin of Life book, and it's doing remarkably well. Great book. And the DVD will be released in about a month's time. So if you want to see it in action on video, that's coming out very soon. Jay Richards has a Ph.D. with honors in Philosophy and Theology from Princeton Theological Seminary, and he's still a Christian, so congratulations. He's not the only one. Many have survived Princeton Theological Seminary. He's a senior fellow at the Discovery Institute, and he alternates with Steve Meyer as the president of the Discovery Institute. Year to year, they alternate. He has authored and edited several books, including Are We Spiritual Machines? And one that I really enjoy is Ray Kurzweil versus the Critics of Strong Artificial Intelligence. Guillermo Gonzalez, he has a Ph.D. in astronomy from the University of Washington. Did postdoctoral research at the University of Texas, and following that, he went back to the University of Washington. He is currently assistant professor of astronomy and physics at Iowa State University. He's authored over 60 peer-reviewed papers. His research interests include the abundance analysis of stars in our galaxy and of the galaxy itself, of the parent stars of extrasolar planets, and is personally responsible for developing many of the new design evidences for our solar system and our galaxy. We're going to have a Q&A session afterwards. We do have one rule during the Q&A time. I'll moderate the questions, and you can address them to any one of us. But please, one question per person per turn. We all have failing memories, and we really want to make sure everyone has a chance to participate in that discussion. So who's going to start first? Jay's going to start first.
Thanks, Hugh. It's great to be with you, and it's fun to now be able to talk about this topic with the book actually being out. Guillermo and I have been lecturing on this for, I guess, 3 full years while we've been working on the book, and so it's all sort of been promissory lectures. We're going to, it'll be in the book. Trust us. We're just going to kind of illustrate it here. But there's something about our argument you should know up front, and it is what philosophers call a cumulative case argument. And that is a technical word which means it's hard to give a lecture in 45 minutes on the subject. Basically, a cumulative case argument means that it's the sort of argument, for instance, that a prosecuting attorney often will use, in which you have multiple pieces of independent evidence, which you try to bring together to substantiate some sort of overall pattern or conclusion, so that any individual piece of evidence might be chalked up to coincidence, but at some point, the cumulative case becomes strong enough that it favors a particular hypothesis. Now, there's no mathematical formula for saying when do you reach that threshold, right? You can't quantify it in that sense, but at some point, it does become unreasonable not to infer to a particular conclusion. And so that's what our argument is like in the book. So we try to establish a particular pattern that we argue is pervasive throughout the universe and that can be detected by studying particular conditions that we find on the Earth. And so remember that. Our argument is about a particular pattern, and it takes a little bit of setup to see what that is. And so all we can do today is give you a couple of illustrations of our argument so you can see where we're going. We can't, if you're slightly skeptical, I hope you won't, the fact that you're skeptical at the end of the lecture, I hope you'll realize, yeah, we recognize fully. All we can do is give you a couple of examples of what we were able to develop more fully and in more detail in the book. But it's nice to actually have a book that we can point you to in case you want to know more. Well, the book, The Privileged Planet, was written, and it is in some ways, at least logically, a polemic against a very popular prevailing intellectual orthodoxy in the physical sciences, and in particular in physics and astronomy. And it's an idea known as the Copernican principle. Now, it turns out the Copernican principle has very little to do with Copernicus himself, whom most of you will recall was the fellow in 1543 that suggested that the Earth is in fact one of the planets and orbits the sun with the other planets, as opposed to the celestial bodies orbiting around the Earth with the Earth stationary. Well, that was Copernicus's idea. It had nothing to do with the Copernican principle per se. But sometime in the 20th century, this idea that I'll tell you about was attached to Copernicus. Perhaps the most sort of popular manifestation and most articulate manifestation of this comes from the late, great Carl Sagan. How many of you have seen this picture that's up here on the slide before, if you can even tell what it is? But it's come to be called the pale blue dot image. But this is a picture from Voyager 1, which was taken in 1990. If you recall, there were 2 satellites sent out to take pictures of the outer planets of the solar system. It reached basically the orbit of Pluto in 1990, about 4 billion miles away. Carl Sagan went to NASA and persuaded NASA to spend time and energy having Voyager turn its gaze back toward the inner solar system to take a picture of the inner planets, which of course are Mercury, Venus, and Earth. But the most important picture, obviously, was the picture of Earth. And you can barely see it here, so we have this little arrow. It's a tiny little speck. Sagan said he was going to use this image to essentially help teach us how fragile we are on this small planet, and that we ought to take care of ourselves and ought to take care of the planet. But in fact, Sagan used this as a metaphor for this idea of the Copernican principle in his famous book, Pale Blue Dot. And here's what Sagan says in that book about that image. Because of the reflection of sunlight, the Earth seems to be sitting in a beam of light as if there were some special significance to this small world. But it's just an accident of geometry and optics. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity and all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. I understand Sagan wasn't a fun guy to party with things like this. But you get the idea, don't you? This is a very articulate expression of the Copernican principle, which simply says there's nothing special or exceptional about our place or time or status in the universe. Whatever has happened here has certainly happened countless times elsewhere. As a scientific hypothesis, the Copernican principle says we should assume, unless we have very strong evidence otherwise, that the Earth is in a mediocre location. The properties of our planet, of our physical location, of our time in the universe are unexceptional. They're not special. The Copernican principle also takes a more robust kind of metaphysical form, and it basically says our metaphysical status is as unimportant as our physical location. Okay, so there's this connection between the mediocrity of our location, of the properties of Earth, of life arising on the Earth, and our metaphysical status in the scheme of things. And so it becomes this sort of, it's sort of a grand articulation of the materialistic worldview as it manifests itself in the physical sciences. So materialism manifests itself somewhat differently in the various sciences, but I think in astronomy and cosmology and physics, it manifests itself as this Copernican principle. Well, what's interesting, I said that you can treat this as an empirical hypothesis. That is a claim that's open to testing, that it can be confirmed or it can be contradicted. And in the book, The Privileged Planet, we just decided to test this particular claim, both with respect to its empirical assertions and its metaphysical implications. And so you can imagine The Privileged Planet is simply seeking to answer this one question. Is the Earth really an insignificant speck in a vast and meaningless universe? That is, are the deliverances of modern science, the things about which we're the most certain, the things that we've learned in the 19th and 20th centuries about the things it takes to make an Earth-like planet, do they confirm this claim or do they not? We think that a theory, to be a good scientific theory, as the philosopher Del Ratch put it, ought to be put in empirical harm's way. There ought to be some way in which nature can speak to your theory, can tell you if you have reason to think it's true or not. We think the answer, in fact, is quite otherwise. And there are a couple of sort of setup points to see why this is so. And many of you have heard Hugh Ross speak over many years or read any of his books, knows that he's talked about many of these things for many years. But just let me give you the way the kind of argument goes so that you hopefully deflect misconceptions. Well, initial schoolboy impressions are that, well, great, it's interesting how life is here. It's interesting the way our sun is here. But, in another environment around, say, a red dwarf star or something like that with different kinds of planets, life will simply evolve to use whatever is available. So whatever elements are available, whatever solvents are available, whatever the source of energy is, life will simply evolve in those ways. And that's an idea that's sort of nurtured by science fiction, So you have these beings that are sort of floaters made of hydrogen clouds and big gas giants or something like that. The problem is this is not at all scientifically feasible. So that even, for instance, the academics that are most optimistic about the existence of extraterrestrial life make some very basic assumptions. They assume that if complex life exists elsewhere in the universe, it almost certainly exists in the presence of liquid water, and it is almost certainly based on carbon chemistry. I cite simply a single example of this. Last week, Seth Shostak of the SETI Institute on space.com wrote an article about the importance of water. Now remember, this is a person that represents an institute which is very optimistic about the existence of ETs. But they nevertheless recognize the importance of carbon and liquid water for life. This is a very long subject, but I just want you to sort of see why this is important. Many properties that the element carbon has that no other element matches. I mean, there's not even a distant second. Often folks will talk about the properties of silicon, but there's really nothing like carbon in its capacity for creating complex, information-bearing, rich molecules, and molecules that are metastable. That is, they're stable enough that they don't fall apart under just any old conditions, but they're not so stable that they can't enter into all sorts of very interesting and important chemical reactions. Carbon is very, very important. Water, on the other hand, is often called the universal solvent, and it's called the universal solvent for very good reason. There's a suite of so-called anomalous properties that water has that other substances don't have that make it ideally suited for carbon chemistry. So you have this one compound and this one element, which together seem perfectly fit for the existence of complex chemically based life. And I'll give you just one example of that. Liquid is water over the same narrow range of temperatures over which carbon chemistry is most reactive. So these are ideally suited for the construction of biological organisms. And so this is the reason that even SETI has the expectation that if we find life elsewhere in the universe, it's almost certainly going to be similar to Earth life, at least at the biochemical level. I mean, this is why we spent $830 million on these probes to Mars, looking for evidence of past liquid water on Mars' surface. It's because water is almost certainly a necessary condition for the existence of life, even if it's not a sufficient one. Now, why is this important? It may be interesting academically, but what this means is that the things we learn about life on Earth, this tiny little pocket in the observable universe, can be universalized so that we can talk about what any sort of habitable planet is going to need to be like to host complex life like ourselves anywhere in the universe. So it's not as if we merely have a sample size of one, because the laws of chemistry and physics are universal. It's not like chemistry is a poorly understood science. We're not looking for other elements to plug in between the elements on the periodic table. So far as we can see in the observable universe, these laws obtain, so that we can generalize about the life we find here to life elsewhere, at least at the biochemical level. That's a crucial assumption in our argument, but we think it's a very, very reasonable one. Well, we've recognized for a long time the importance of liquid water to construct a so-called habitable planet. A habitable planet, and Hugh talked about this briefly yesterday, simply the kind of planet you need to be able to be inhabited by complex beings. Not just any planet will do. And at least since the 1950s, the presence of liquid water on the surface of a star has been widely understood. You need a planet in the so-called circumstellar habitable zone, in the Goldilocks zone around the right kind of stable star, so that liquid water is not boiling off or freezing on the surface. And so, of course, the Earth is in this circumstellar habitable zone, this nice nearly circular orbit around a stable star where liquid water stays on its surface. But in recent years, we've come to realize that you need a whole lot of other things. And many of these things have been speculated about, but it's now very much a part of the discussion in astrobiology. Just how many things need to go right to create a habitable planet? Well, this is just a list, and Hugh had a list yesterday if you heard his talk, so I'm not going to spend a lot of time on this. And some of these things are more controversial than others, but this is a list of the things we think are very defensible, that are very difficult to get around if you want to build a habitable planet. You're going to need to have a terrestrial planet, that is a rocky planet like the Earth. A gas giant planet is not going to work. The planets that we found so far around in other star systems are large gas giants. They're not going to be habitable. You need a terrestrial rocky planet, probably with the same general composition and same general size as Earth to retain its atmosphere, to have the right kind of geology and a number of other things that you need. So you're not going to have a terrestrial planet that's 4 times larger or 4 times smaller than the Earth. It's going to be something like the size of the Earth in its composition and its size. You need a stabilizing moon, which Hugh mentioned yesterday, to stabilize the tilt of the planet's axis. If the Earth didn't have a moon, we would be like Mars, which has 2 very anemic sort of asteroid-like moons. The Earth would wobble on its axis from 0 to perhaps 60 degrees over time. It would create essentially catastrophic climate patterns on the surface of the planet that would not be hospitable to complex life. It also distributes the tides and the nutrients that are mixed from the continents to the oceans and the circulation of warm and cold waters around the surface. So you need a moon, which is something that, at least in terms of our actual knowledge of this, is a recent discovery. You need plate tectonics, which plays a crucial part in the carbon cycle, which recycles the elements that life needs back up into the atmosphere where they can have access to life. You need the right kind of atmosphere. Not just any atmosphere is going to work for complex life. You also need the right kind of geology in your planet to produce the right kind of magnetic field to protect the atmosphere from stripping from particle radiation from the sun. You need the right kind of planetary neighbors, like the gas giants in the outer part of the solar system, which they act like offensive linemen for the inner solar system to protect it from too much bombardment by outlying comets. You need the right kind of single star. Many star systems are doubles, binaries, or triplet star systems. It'd be almost impossible to get stable planetary orbits in a system like that. So you need a single star, and you need the right kind, probably, of sun-like star. It's the kind of star you want for life is probably very much like ours. You need the right kind of galaxies you talked about yesterday, probably a medium-large spiral galaxy like the Milky Way, and you need to be in the right place in the galaxy. Not just any spot is going to work with life. And you need to be in the right cosmic time. Early in the history of the universe, there's not going to be any habitable planets constructed, and it's also going to be very hostile with respect to the radiation and the sort of events that are going on. And there's also going to be the vast majority of cosmic history is going to be uninhabitable. So if you think of, we think of cosmic history as going from t equals 0 to the present. Well, cosmologists often talk about timescales from t equals 0 to t equals 10 to the 150th out in the future. And so when you're thinking about those size scales or time scales, 15, 20 billion years is a very, very narrow slice of time. And that's when you're going to need to be in time, where you're going to need to be able to have a habitable planet. And as you talked about, you're going to need to have a universe that's fine-tuned for life. You're going to need to have the right sorts of initial conditions and the right sorts of physical laws, the universal laws that govern the universe as a whole, are going to need to rest on a razor's edge for complex life to be so much as possible. Okay, well, that's just a brief run-through of what is one pillar of our argument in the privileged planet. Now, I want to do a little intellectual exercise with you for a moment, because we've recognized, Guillermo and I, a sort of dilemma in this argument, because for a long time, Guillermo and I are theists, and so we believe in design generally, and I've found the design arguments in cosmology for the fine-tuning of the laws of physics plausible, and the arguments in biology plausible for a long time. But there's a dilemma when you're arguing about design and you're trying to base it on the production of a habitable planet. Okay, so I want to try to get you to appreciate this dilemma a little bit. So what I want you to do is I want you to separate out the question of the fine-tuning of the laws of physics for now. So that's going to be a given. All right, and so the question is whether or not chance has enough resources given the laws of physics to produce a habitable planet. Okay, so what we're going to take as given is the law of gravity and electromagnetism and all those things. So given the universal parameters that the universe has and its size, is it possible that while habitable planets are likely exceedingly rare because of all the things you need to have, nevertheless, chance has the resource to produce actually one? And I framed this using a term that Bill Dembski, I think, originated, which is the idea of probabilistic resources. The question is this: with so many probabilistic resources that we know about now, this isn't multiple universes to which we can have no access, but resources in a very large universe. We know there are something on the order of, say, 100 billion to 300 billion stars in the Milky Way, and perhaps the same order, 100 to 300 billion galaxies in the observable universe. So there are a lot of chances in the universe for producing a habitable planet, and all those chances are going to be constrained very narrowly by the laws of physics, right? You're not going to get rectangular orbits and things like that. I mean, there's only certain things that are even possible. So chance is already going to be highly constrained. We've got a big universe with lots of chances. And the question is, how do we tell if a habitable planet like Earth is the result of chance or purpose? And let me just sort of explain the dilemma here to you. Many of the terms, I ran through a list of the things you need to get a habitable planet. Some of these things, we have a sense of what the probabilities are, but others, we simply don't really know the values of the terms. I mean, Guillermo and I, and many of us, and I know Hugh, suspect that these probabilities, say, of getting a large, well-placed moon, are very, very small. But we don't know. It's not like it has the status of knowledge what the probability is. And so here's the dilemma, and this is how we do it in the book. We say, let's say we're going to assign a very optimistic probability to all these things. So we're going to give chance, the benefit of the doubt here, and we're going to say there's a 10% chance of getting a terrestrial planet in your system. There's a 10% chance of having it be in the circumstellar habitable zone. 10% chance of getting a moon. 10% chance of getting gas giant planets. You see the situation. Well, we think at least 13 independent variables that you need, probably more, okay, to get that. But we're going to just base this on the stuff that we are most certain about. Well, you run this calculation, and you end up with 1 chance in 10 to the 13th of getting a habitable planet in the observable universe. Now, remember, these are all optimistic estimates, but when you don't know the exact values of terms in probability, you want to assign optimistic probabilities, right? And so this seems impressive, right? It looks like, well, that right there, being very optimistic, would mean 1 in 10 to the 13th of getting a habitable planet. Well, there's something like 10 to the 11 stars in the Milky Way galaxy, maybe 3 times 10 to the 11, but let's just go with this because it's easier to hold in your head. Well, that would mean that there's less than 1% chance of having just one habitable planet in the Milky Way galaxy, even on very optimistic estimates of the probabilistic resources. Well, does anyone know what the problem is here? I mean, does that mean, therefore, design at this point? I mean, it must be design, because look at the chances here, less than 1%. The problem is that we haven't taken account of all the probabilistic resources. There are probably about 10 to the 11 galaxies in the observable universe. And why is this important? Well, let me give you an illustration. Imagine that you walk into a room and you see me flipping this quarter here, and Hugh used a Canadian coin with what? Hugh, what was the ducks? Beavers. Yeah, that's right, beavers. I'd never heard that, and I live an hour from the border of Canada. I didn't know about this, but I've got an American coin here, and you walk into the room and you see me flip the coin 20 times, and I get 20 heads in a row. All right, what are you going to think about the coin, obviously? It's rigged, right? I hope, if you have any probabilistic intuitions at all, you're going to bet that this is rigged. And you say, let's have a bet. Okay, now what if the scenario is different, though? What if we're the victims of some strange fraternity prank, and we're locked in our dorm room, and the rule is that they're going to slide the food in the water under the door until we get 20 heads in a row. And so we're in there for a month, flipping the coin over and over, and I get really good and get up to 100 flips a minute, 12 hours a day. And so I get a few million of these off in a couple of months. Now, if at some point during these 2 various tedious months I get 20 heads in a row, are you going to be able to infer anything in particular about the coin? No, I mean, it might be rigged. It might be. It's not as if you know it's not. But you're not going to know for sure. Well, what's changed is the probabilistic resources available, which are that's going to change your impression of what you can infer based on the probabilities, on the fact that a rare event happened, of course, but on the other hand, you had a lot of probabilistic resources available. And this is sort of an intellectual dilemma in this case, because we have a sense that the production of a habitable planet is likely to be exceedingly rare. But on most of the terms, we don't have exact probabilities. And so there's a degree of uncertainty as to whether or not the probabilities, the resources available, suffice to allow chance to produce this. to produce a single habitable planet. And this is the reason that some smart people like Don Brownlee and Peter Ward, who wrote the book Rare Earth, are able to say chance. I mean, it's intuitively, it seems strange to people when they hear this, but there's some integrity in this argument simply because they're saying, look, the universe is a very big place. We're not postulating these airy-fairy multiple universes. We're talking about all the stars we know about. And yes, we grant that habitable planets are rare, but the universe is a big place. Maybe this could happen once. And so that's the sort of intellectual dilemma that we wanted to deal with in the book rigorously. And so the conclusion that chance, in principle at least, has a lot of room to operate. So unless we can really nail down the probabilities and exhaust the resources of the universe, it's difficult to know whether the production of a habitable planet would be in some way evidence of design, or whether it would be simply at the level in which we abstract the universal fine-tuning could be produced by mere chance. Well, the book about In the Privileged Planet is about much more than this, because The Privileged Planet, we attempt to resolve this question, to say there's something else, or to ask the question, what if there were something else in addition to the rarity of habitable planets that we could learn? Is there something we could learn that would give us a way to tell, that would suggest conspiracy rather than mere coincidence? That is the issue and the difficult question we try to resolve in The Privileged Planet. And I'm going to hand it over to my co-author, Guillermo Gonzalez, to tell you what this other thing is, what this other pillar of our argument amounts to.
All right. I'm a little shorter than Jay. Okay, thanks a lot. So I'm going to give you the other pillar of our argument. So our argument actually rests on two pillars: habitability, or the conditions you need to have a planet that can host complex life, and measurability. And we claim there's a pattern in the universe, wherever you look, at least in the physical sciences that we examine, astrophysics, cosmology, geophysics, that where the places are most habitable, they also offer the best opportunity for measuring things about the universe. Put it another way, the same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries. The very conditions that make Earth hospitable to intelligent life also make it well-suited to viewing and analyzing the universe as a whole. Now, since this is a cumulative case argument, it's empirical. We look out at the world and we just ask the question, what do we see? What patterns do we see? That's just science. And one of the patterns that I claim that we see is that habitability correlates with measurability. And we claim this is a surprise. So the first 10 chapters of our book are basically just presenting the empirical evidence over a wide range of scientific disciplines, from geophysics to atmospheric sciences to planetary sciences, to stellar astrophysics to galactic astronomy, cosmology, and we even have a chapter on the fine-tuning of the laws of physics. Unfortunately, I don't have time to go through every example. It would take us probably 6 hours. And that's one reason the book is 444 pages long. So I'm just going to present a couple of examples. But first, let me just run through the examples that we do present very briefly. So the first chapter is on perfect solar eclipses, and I'll have more to say on this one in a little while. Turns out the Earth is the best place in the solar system to view total eclipses of the sun. Is that just a coincidence, or is there a deeper meaning to that? The Earth's surface is also the best recorder of information in the solar system. You can think of the Earth's surface as containing literally millions of little data recorders or strip chart recorders, constantly recording data about the environment automatically and archiving that information for later retrieval. That seems like a surprise also, just based on, if you want to use a Darwinian explanation for how we got here and how the Earth got here, why should the planet contain all this very rich information, these vast archives of information? That's a surprise. So is that just a coincidence? Plate tectonics, that has a role to play both in life on Earth, as Don Brownlee and Peter Ward argued in their book Rare Earth, but in addition, it makes the Earth a very measurable place. We can measure the interior structure of the Earth because of earthquakes. And plate tectonics is also related to the generation of magnetic field in the Earth through the flow of heat to the Earth's interior. And as Jay mentioned, a magnetic field is necessary to make a planet habitable for complex life. Well, at the same time, a magnetic field serves, you might say, as a global positioning system. And for those of you who know a little geology, the study of paleomagnetic fields has been extremely important in figuring out the Earth's geologic history and choosing between the old geosynclinal theory and the plate tectonic theory. The amazingly information-rich magnetic reversals recorded on the ocean floor has been absolutely crucial in distinguishing between those theories. The transparency of the atmosphere. That's a particularly simple observation that everybody can appreciate. If it were not for the fact that the atmosphere is transparent, we would not know about the stars beyond the Earth or the other planets, or we wouldn't have a subject of cosmology. We couldn't ask questions about origins of the universe. And it all rests on that one little coincidence that the atmosphere is transparent. Of course, for existence, for survival, for a Darwinian type explanation, all you need is a merely translucent atmosphere, right? Photosynthesizing plants don't need to observe stars. Okay, all they need is to detect photons. And for that, you just need a translucent atmosphere. So again, another surprise. Is that just a coincidence? Our planetary neighbors, and by that I mean the other planets and the moon, they played surprisingly important roles in maintaining the Earth habitable, and they've also helped in science, especially the development of gravitational theories, starting with Kepler, his observation of, or his determination of 3 laws of planetary motion, and then Newton with his universal law of gravitation, and Einstein with his general theory of relativity, all depend to a surprisingly high degree on the particular circumstances of the solar system we find ourselves in. Okay, astronomy gave birth to physics, not the other way around. Stars. Turns out stars are remarkably information rich as well with their spectra. You can think of stars as literally probes that transmit information back in all directions. And so they serve as a particularly important probes of the universe. Our location in the galaxy, and also I'll have something more to say about this one a little later, so I'm going to skip that for now. Cosmic time. Again, Jay mentioned that you have to live in a certain time in the history of the universe. Not too early, when the radiation levels were far more intense and the heavy elements were still not abundant enough to make Earth-sized planets. And not too late in cosmic history, when the star formation rate has declined, and so you don't have sun-like stars around anymore. You just have dim red dwarfs, and also the radioactive elements that are necessary to drive plate tectonics will have decayed in a few billion years. And finally, you need a fine-tuned cosmos. And we relate the particular laws of physics and constants of nature with some examples to our ability to do science in the universe. And one person who's actually talked about this before us was Paul Davies, and also John Barrow. John Barrow noted that it's only in a universe with 3 spatial dimensions that you can have stable orbits, and you can have electromagnetic radiation transmitted with high fidelity. Paul Davies has talked about the separability of the laws, how the different fundamental the forces, rather, of physics are separable. They have different ranges of operation, so we can study them separately. You don't have to understand the whole universe all at once to understand a part of it. You can understand it piece at a time. And we can do that because the universe is of a certain type with certain laws of physics. And that's all I have to say on that one. So again, I'm just going to go into detail on 2 of these examples: perfect solar eclipses and our location in the galaxy. And in fact, it was a total eclipse of the sun that I went to see in India in 1995 that actually inspired me to come up with the privileged planet hypothesis. So I'm going to give you a little story because this is my understanding how my inquiry started. Perhaps you might understand what it is that motivated me and inspired me to come up with this idea. So in 1995, I went to see an eclipse of the sun in India. It was my only one still. I grew up as an amateur astronomer, and I've always wanted to see a total eclipse. How many of you have seen a total eclipse, by the way? Okay, a few. I think you'll all agree with me, those of you who saw it, that it's a very inspirational and emotional event. It really is an event for all the emotions. And I've talked to eclipse chasers, people who try to fit as many eclipses into one lifetime as possible. And they've all told me the same thing. Wherever they go, no matter what the level of education of the natives, they have the natives standing next to them. And they'll both be observing the eclipse. They'll both be equally in awe and often in tears. So it doesn't matter what the level of education of the person is. It's an inspirational event. There seems to be something about eclipses that knowing how to predict the circumstances of the event anywhere on Earth to within 1 second of time does not remove. Okay, there's something deeper about it. So I went there to do an experiment during the eclipse to measure the changes in the atmosphere during the eclipse, but that's not what inspired me to present the privileged planet hypothesis. At the same time, I had been thinking about what you need to make a habitable planet. I had been reading on the circumstellar habitable zones, and so I had these two ideas in my head: solar eclipses, circumstellar habitable zones. And I knew that the Earth was the best place to view solar eclipses in the solar system. And I knew that the Earth was the most habitable place in the solar system. So I thought, well, these two link, these two are coincidences that link on the Earth. Is that just a coincidence, or can you make a bigger or a deeper, find a deeper explanation for this? Okay, that was my hypothesis. But before I get into the details of that, let me give you a little background on eclipses, just some Astro 101 background on total eclipses. To produce an eclipse, you need a luminous body, an eclipsing body. So the luminous body in our case is the sun. An eclipsing body is the moon. An observer platform, in our case the Earth's surface. The right distances apart, and all in a straight line in space. So here's a slide I borrowed from my Astro 101 lectures where I explain eclipses. And so it's just showing the moon in orbit around the Earth. And when it's in alignment with the sun, so the sun, the moon, and the Earth in a straight line, the moon casts its shadow on the Earth, and it races across the Earth's surface. The darker part of the shadow is called the umbra. And you notice it's pretty narrow, it's pretty thin. And so it's a thin track, only 100 or 200 kilometers thick. So you have to be along that narrow track to see the solar eclipse. Now, if you know a little bit about geometry, you immediately recognize that the reason the shadow, the umbra, is focused right at the Earth, almost exactly, is because the moon and the sun subtend almost exactly the same angle in the sky. Okay, they're both about half a degree across, but they're very different objects. All right, so of course people have noted this coincidence for centuries. You know, the moon appears almost exactly the same size as the sun in the sky, even though the sun is 400 times larger. It's a very different kind of object, but it's also 400 times farther away. Okay, so therefore they both subtend the same angle in the sky. And just to illustrate that, here's a telescopic picture from the 1995 eclipse with a disk of the sun superimposed in the middle with some Photoshop editing. So you wouldn't actually see this during an eclipse, but I just superimpose it for illustration. So you can see how close the sun matched the moon's disk. You can see the moon's disk, that black edge there. And you can see the inner part of the corona of the sun here and some prominences. Now, I've also indicated here with these little arrows the range and size of the moon relative to the sun, because the moon's orbit is not a perfect circle, it's eccentric. But what's interesting is that if you take the average value of the size of the moon, it's exactly the same as the sun. So the two match to a very high degree. Now, that particular eclipse I went to see lasted 51 seconds. It lasted long enough to see the stars come out, and the brighter stars and the planets. And you can, because of the close match, you can study not only the corona of the sun, but the very thin inner layer of the sun called the chromosphere. It's called, which means color sphere, okay, which looks pinkish to the naked eye. So I asked, well, there are lots of moons in the solar system. So what's so special about eclipses on Earth? You know, all you need is the sun, a moon, and a planet on which you can project the shadow. Surely this must happen on other planets. Well, indeed, you do get eclipses on other planets. So let me illustrate that to you a little bit. But there are eclipses, and then there are eclipses. They don't all come in the same variety. So here on this plot, I've arranged in order of distance from the sun all the planets with moons, starting with the Earth, ending with Pluto. And on the horizontal axis here, I have the angular size ratio of the satellite or moon relative to the sun. And it's a logarithmic scale. So what this means is that if it's 1.0, then it's an exact size ratio between the satellite and the sun. They both subtend the same angle on the sky as viewed from an observer on the surface of a planet. Now, if you're less than that, then the moon is much smaller, or the satellite is much smaller than the sun. If it's on the positive side here, on the large side rather, then the satellite is much larger than the sun. So I call these super eclipses, where the moon is much bigger than the sun. So you notice immediately that there are two that cross this vertical line, Earth's moon right down the middle, as I had noted, and then Prometheus just barely crosses it. That's small potato-shaped moon around Saturn that whips around real fast. It's one of the shepherd moons. Eclipses from that would last about a second or so. Now, you can see a trend here as you go out from the inner solar system out to the outer solar system. The average location of these moons, these bars, shift to the right. That makes sense because as you go out away from the sun looks smaller and smaller and smaller in the sky. So we'd expect the average size moon to be larger compared to the sun as you go out. So given all the moons of the giant planets, it's not surprising that by chance one of them crosses the line. Another interesting thing to notice is that the Earth and Mars are the only inner planets with moons, but the two moons on Mars are thought to be captured asteroids. They're very small. And so you only get, in fact, they're not even called partial eclipses, they're called transits, okay, for the moons around Mars. By the way, these have bars because I've taken into account the eccentricity of the planet's orbit and the eccentricity of the moon's orbit, the fact that they're not perfect circles. Okay. Now, the other unusual thing about Earth's moon is that, well, it bucks the trend, right? It's this very large moon around a terrestrial planet. Venus doesn't have a moon. Mercury doesn't have a moon, so that's already anomalous. And it bucks this trend. It's very large in comparison with its planet, and it matches the size of the sun. It bucks this particular trend. And by the way, here are the 4 Galilean moons, which some of you may have seen if you look through a small telescope at the planet Jupiter. They cast shadows on Jupiter, but they're all super eclipses. They'll be much larger than the sun appears. And by the way, eclipses on Earth are better than other places for other reasons. They last longer, up to 7.5 minutes from Earth, because the Earth is a relatively low-mass planet, whereas the giant planets are very massive, and so because gravity is much stronger, the moons whip around those planets very quickly, and so the eclipses don't last very long. Also, the moon has one of the roundest measured profiles in the sky, so you get very, very symmetric eclipses. And finally, it's the planet closest to the sun that has a moon, and so the sun appears larger on the sky during eclipse from the Earth than from any other planet. So a lot of these factors converge to make the Earth's surface the best place in the solar system to view solar eclipses. And by the way, there was historic images taken recently by the rover, one of the rovers, Opportunity, on Mars recently. This is a picture of Deimos transit or eclipse and the Phobos transit or eclipse, March 4th and March 7th, 2004. And it's just to show you how much smaller the moons look from the surface of Mars compared to, say, our eclipses. So they're quite inferior. Again, they're often even just called transits. Now, what's interesting about eclipses is that they provided us opportunities for making certain important scientific discoveries. In fact, much of professional astronomy in the 19th century was involved with eclipse chasing, going to distant lands to observe eclipses of the sun, to learn about the sun's atmosphere, and to learn about the physics of the sun. One of the things that was particularly important, there were several things they learned, but one of the most important things was the fact that we can observe the chromosphere of the sun during a total eclipse of the sun. And remember, I said because of the very close match between the moon and the sun, we get a very good view of the chromosphere, which is a very thin layer in the sun. Now, why is that a big deal? Well, let me give you a little background first on spectroscopy. Of course, you're all familiar with spectra because I think you've all seen rainbows, right? A rainbow is just a spectrum of the sun, a low-resolution spectrum produced by droplets in the Earth's atmosphere. And by the way, the Earth's surface is the only place in the solar system you can view rainbows from. It's another interesting coincidence. There's 3 types of spectra. If you look at a hot, dense source, you get a continuous spectrum. If you look at a gas at some temperature in space, you get an emission line spectrum, a low-density gas. Now, if you pass a light from that hot source through the gas, you get the continuous spectrum with absorption lines superimposed at the same locations you would have seen the emission lines. Okay, these are the 3 basic types of spectra that astronomers understand are produced at different locations in the universe. Now, the thing about the sun is that its absorption line spectrum here, which is composed of thousands of absorption lines, and it's what you normally see when you look at the sun at any average afternoon, They didn't understand where those absorption lines were produced, and they didn't understand where they were produced in the sun. Okay, that was a mystery. Until Young, a famous solar astrophysicist of the 19th century, did an experiment during an eclipse in 1870 where he looked at the sun through a telescope with a prism. So he basically looked at the spectra of the sun during the eclipse just before totality and just before the photosphere of the sun was completely covered. So I'm going to animate a picture that was taken in 1905 illustrating this effect called the flash spectrum. And before his eyes, the sun's spectrum changed from an absorption line spectrum to an emission line spectrum. That didn't happen that fast. It happened over a few seconds, but he literally saw transform before his very eyes the sun's absorption line spectrum into an emission line spectrum. And he finally, in that instant, understand how the sun's absorption line spectrum is produced and what part of the sun produces it. It's the gas in the chromosphere. The reason it turns into an emission line spectrum is because the moon obligingly covers up the bright photosphere, which produces the background continuum light and allows us to see that low-density gas around it, which is responsible for imposing those absorption line spectrum on the sun. And so that experiment, that beautiful natural experiment, is what finally allowed astronomers to figure out how the absorption line spectrum is produced in the sun, and therefore other stars, because of course all we can see from other stars are their absorption line spectra. We can't resolve them into disks; they're too far away. Perhaps a little easier to understand example of how eclipses were important in science is testing general relativity. In 1915, 1916, Einstein proposed an important test of his new theory of general relativity. Of course, he knew about the precession of the perihelion of the planet Mercury, but that's not quite as convincing when you develop your theory after a particular observation. Okay, that's called the problem of old data or the problem of old evidence. What's perhaps a little more important or a little more convincing to people is if you can make a completely new prediction from your theory and then test it. And so he made a prediction that you could look at stars around the sun if you photograph the sun during a solar eclipse and measure their positions, and then come back to that same part of the sky 6 months later when the sun is out of the way and photograph it again, and you'll see that the stars are in different positions. That's because when starlight passes near the sun, it gets bent, okay, because the sun's mass bends space-time around the sun. And that was confirmed by Eddington in 1919 and subsequently by many other experiments during solar eclipses. And that was a particularly important confirmation because it led to the very rapid acceptance of general relativity in the early 20th century. Okay, so concluding this section, the requirements for producing perfect solar eclipses which provide scientific insight also contribute to Earth's habitability. This is only one example where the conditions for habitability overlap the conditions for measurability. Now, why can I say this? Okay, I haven't told you the rest of the story. This is where it really gets interesting. Okay, these two things converge on the Earth's surface: the best place to view solar eclipses in the solar system and the most habitable place in the solar system. Is that just a coincidence? Well, I said that when I went to India, after I came back from India, I had these two ideas in my head: my solar eclipse experience and my readings on the circumstellar habitable zone and other things you need for habitability. Well, as it turns out, you need to be in a certain place around the sun to have liquid water on the surface of a planet. Jay already discussed that. It's called the circumstellar habitable zone. That establishes how far away you must be from your host star. Therefore, that establishes how big your host star will appear on your sky. Okay, that's the first link to eclipses. Because remember, to get eclipses, you need to have your light source a certain size on your sky, and then you need to have an occulting body, an eclipsing body, a certain size on your sky. Okay, so what about our occulting body? Our occulting body is the moon. And again, as Jay mentioned, the moon makes the Earth much more habitable by stabilizing the tilt of its rotation axis. And so the mere presence of the moon makes it much more likely that you will have observers on a planet. Okay, so this is this striking overlap between the conditions for habitability for the Earth, two very critical conditions: the circumstellar habitable zone, the presence of a large moon, are also the two of the most important conditions for producing solar eclipses. And so we conclude that if there are other civilizations and other planets, they would be more likely than not also to observe solar eclipses. Okay, and so that was the first instant of what we're calling the correlation between habitability and measurability. Okay, and it's at the level of the laws, although instantiated through stochastic processes in the universe. So at the level of the laws, namely, wherever you find a planet that's habitable with liquid water on the surface, or on a star that optimizes the habitability of complex life, an early G main sequence star, then you're also going to have a large moon around that planet, and so the overlap of these conditions makes it much more likely than not they're going to observe solar eclipses. And so that started an inquiry into, or actually, we present it as a hypothesis, and it's called the privileged planet hypothesis. And the privileged planet hypothesis is what I stated earlier, that habitability correlates with measurability. But again, it's a cumulative case argument. Perhaps eclipses is just a fluke. It's just an accident of the way things turned out, because it's just one example. So we wanted to see if this generally follows in the other sciences. And so we studied this and all those other examples that I showed you earlier in that list. And one of the other examples is our location in the galaxy. In 2001, I wrote an article in Scientific American with my colleagues Don Brownlee and Peter Ward. It's in the October 2001 issue of Scientific American, if you're interested, where we presented a new idea called the Galactic Habitable Zone. And that's that place in the galaxy where the conditions for life are optimal, okay? And it turns out not every place and time in the galaxy is equally habitable. So let me just go over briefly what conditions you need to define, or what goes into defining the Galactic Habitable Zone. I'll abbreviate that GHZ. Okay, so there are two broad categories of phenomena that go into defining it. One is the requirements for building a habitable planet in the first place. The Earth is made up mostly of silicon, oxygen, magnesium, and iron. Okay, those elements have to come from somewhere. Okay, astronomers think they come from supernovae. Okay, you don't have that supply of these heavy elements in equal amounts anywhere in the galaxy. They vary considerably when you go from one place to another in the galaxy. And survival of complex life is the other category of phenomenon. If you have complex life on a planet, it has to survive. There are lots of dangerous things in the universe, and again, these dangers or threats in the galaxy vary dramatically from one place to another. Not every place in the galaxy is as safe as every other. Okay, so let me give you a little Astro 101 background on our place in the galaxy. This is the latest understanding of the spiral structure of our galaxy. We are located between spiral arms, about halfway from the center to the visible edge of the galaxy. We live in a highly flattened galaxy, a spiral-type galaxy type S-barred BC, Hubble type. So it's that means the bulge is relatively small compared to the spiral arms, and it's so the spiral arms dominate most of the light of the galaxy. If you were to see this from a distance, if you have this is basically a bird's eye view of the galaxy looking down, assuming we could have birds 40,000 light years above the plane of the galaxy. So this is important to know that we're actually between spiral arms at this particular location. So that's where we are. By the way, I've seen a shirt with a little illustration of the galaxy, and it has a little arrow pointing, "You are here." I think that's meant to convey our insignificance. Well, I would recommend another shirt with a little arrow pointing to the same place saying, "You must be here." And here are the reasons why. Okay, it turns out there's a trend of heavy element abundance in the galaxy. As you go out from the center of the galaxy out to the edge, the concentration or abundance of these heavy elements that you need to build an Earth-like planet declines. Okay, and so if you go out to the edge of the disk, where the heavy elements are much less abundant, you're much less likely to form a planet like the Earth. Okay. Threats to complex life are much more severe towards the center of the galaxy. Stars are much closer together, more concentrated in the inner regions of the galaxy. Supernovae are more frequent. There's a giant black hole at the center of the galaxy, which is now in a quiescent state, but astronomers believe that from time to time when a star passes near it, it gets ripped up, and so the accretion disk around the black hole gets very luminous, and it emits lots of radiation, X-rays, gamma rays, particle radiation, and so the inner region of a galaxy is filled with a lot of high-energy radiation. But the threats decline as you go out from the center of the galaxy. So there are these two broad trends right off the bat. Okay, the building blocks for terrestrial-type planets, and then the other one is the threats. So we argue that the most habitable place in the Milky Way is a ring about halfway out from its nucleus. Okay, it's going to be a fuzzy ring. It's a probabilistic thing. Okay, we don't think it has extremely sharp boundaries. And it does not include the spiral arms because those are also dangerous places. So you can think of it as a broken ring. Although here, for illustration purposes, we drew it as a continuous ring. So the center is dangerous, and the edge, not enough building blocks for terrestrial-type planets. And here I've just zoomed out the solar system just to remind you about the circumstellar habitable zone. It's also an annulus, presently thought to be between 0.95 astronomical units and about 1.2 astronomical units from the sun. And that's just the requirements for continuously maintaining liquid water on the surface of a terrestrial planet. There are actually other things that go into defining the circumstellar habitable zone, about 3 or 4 other major factors that other people don't discuss, that we discuss in our book, but I don't have time to go in there, so that's just a teaser. It's actually narrower than it's discussed to be in the literature. And there was just recently a paper published on the Galactic Habitable Zone by an Australian astrophysicist named Charles Lineweaver. It's published in Science. I think it was the January 2nd, January 4th issue of this year, where he actually took our model and did some calculations and found that about 10% of the stars in the galaxy are in the Galactic Habitable Zone. But he did not include all the factors. So in fact, I think that's just an extreme upper limit. It's probably even narrower than what he found in his paper. But he basically confirmed our earlier study. So why is that a big deal? Why is it a big deal where we're located for scientific discovery? Well, it turns out to be, for scientific discovery, the Galactic Habitable Zone is very close to the best place in the solar system for making discoveries in galactic astronomy, stellar astronomy, and cosmology simultaneously. First of all, there's very little dust extinction in our region of the galaxy. In fact, it's anomalously low where we happen to be. And dust is one of the main sources of obscuration of distant objects. Okay, there's a lot of dust between you and some other object you're looking at. It's going to look much fainter. Our particular vantage point gives us a very good view, and in particular, the flattened shape of the galaxy is very helpful because that means we have very large fractions of the sky that are not obstructed by dust and gas and nearby stars. Our location right at the midplane of the disk also gives us a very good observing point for a very diverse range of star types and even star formation. And you need to understand stars and how stars, the physics of stellar interiors, before you can understand other galaxies. Because, of course, other galaxies are made of stars, and stars are the primary sources of information from the rest of the universe back to us. And we think most importantly, it's this very asymmetric or non-spherical shape of the galaxy that is particularly important in discoveries in cosmology because it's our off-center position from the galaxy. The fact that we're not at the center of the galaxy, but off-center, and living in a highly flattened galaxy that allows us to separate very successfully the local radiation sources, local objects like stars and nebulae, from the distant cosmological objects. See, the distant objects are uniformly distributed on the sky, spherically. So if we were living at the center of the galaxy or at the center of, say, an elliptical galaxy, which is more spherically distributed, it would be far, far more difficult to separate the local from the distant. And this is an important aspect of astronomy that's overlooked. People just take it for granted. Okay, the fact that we can separate the local from the distant. And this is particularly important in the discovery of the microwave background radiation. The microwave background radiation was the key discovery that convinced most cosmologists in 1965 that the steady state model was wrong and the Big Bang theory was right. It was a very clean prediction from the Big Bang theory, okay, that there would be this microwave background radiation discovered. And that's what finally convinced most cosmologists. And today, it turns out to be the single most important source of information in cosmology. And I'm convinced that we would not have discovered that if we were at the center of the galaxy or near the center of the galaxy because of all the more spherically distributed radiation sources. This is just some data from the WMAP satellite, NASA's WMAP satellite, released a few months ago, and it took data at several frequencies. This is plotted on galactic coordinates, and you can see the galactic midplane here, with red being the most intense at different wavelengths. And here 3 wavelengths were combined to give you a false color picture showing a foreground contaminants on different frequencies. But the point is, it's the highly flattened distribution of the local contaminant radiation sources that allows us to separate the cosmological microwave background radiation from the local sources. In fact, Fred Hoyle in the 1960s, who never gave up on the steady state model, by the way, to his death, argued that because the local radiation sources, the energy density of stars in our galaxy, energy density of infrared emission from dust, the energy density of synchrotron radiation, they're all very similar to each other. They're all about the same level. And he said it was similar to the energy density of the microwave background radiation. So he said, well, maybe it's just a foreground contaminant. Okay, maybe one that we haven't identified with a particular source yet. See, but that never really caught on because of the very different distribution of these radiation sources on the sky. Okay, I'll hand it off to Jay.
Well, remember I asked you the question before I handed it off to Guillermo. What if there was something in addition to the rarity of the production of habitable planets, something we could learn that might suggest conspiracy rather than mere coincidence? Or think of the question this way. Even if so-called stochastic processes produced a habitable planet, so even if the universe, given its highly constrained physical laws and its many, many resources, many opportunities, could produce a habitable planet. This is called, philosophers call this an even-if argument. Would there be something about the existence of these rare habitable planets that would bespeak purpose and design rather than mere coincidence? And so now I think you're probably seeing the gist of our argument. Would it not be interesting to learn that those very rare pockets, those very rare places in the universe where complex beings such as ourselves can exist, were also the best overall places for those beings to discover the universe around them? What if the best conditions for complex observers were also the best conditions overall for scientific discovery? Would that be a fishy pattern? Is that the sort of thing you'd expect on chance? Or is that the sort of thing you'd expect on design? That's the question. I think already intuitively you know there's something fishy there. Unless you've had one too many philosophy classes in 20th century continental existentialism, you know there's something up when you see this. Most people know there's something up as soon as they hear that the best place in the solar system to see solar eclipses is where there are observers to appreciate them. There's just something fishy about that. And we see that at an intuitive level. But of course, when you're arguing for design, and you're arguing for design on the basis of empirical evidence, you're saying this is something that's empirically tractable. You want to move from mere intuition into argument. You want to frame your evidence fairly and reasonably so you have publicly available evidence. This isn't based on a private revelation. This is based on the scientific literature that anyone has access to. And you want to base it on the inference and the argumentative structure to be reasonable for a conclusion. And so in the book, The Privileged Planet, we actually pursue what is probably controversial, but we pursue a pluralistic approach to inferring design. What this means is that philosophers have a number of ways of rationally reconstructing what's called the design inference. And a rational reconstruction is simply a reconstruction that shows that something we do all the time immediately is nevertheless rational when you make it an argument. So when you look at a stop sign, you stop. You don't say, well, what's the probability of the laws of physics and wind and erosion producing a stop sign? Maybe it's just a quantum fluctuation that put it there. You spend no time doing that. You infer design immediately and you stop, hopefully, right? Well, the question is, what is it about, what are the features of those things formally? What are the things about structures that are designed that cause us to infer design rather than merely inferring to some sort of impersonal process? Well, most of us, at least initially, and for actually most of Western history, we thought it really had something or everything to do with probabilities. But William Dembski, the philosopher who's, of course, here, made a breakthrough insight in his book in 1998, The Design Inference. And the design inference, this is a very quick Dembski for dummies. But what Dembski said is there's something in addition to mere improbability that is often a necessary condition for inferring design. Most of you have probably, at this conference, have probably heard this, but so let me give you just a very brief illustration of this. When you go to the Black Hills of South Dakota and you see Mount Rushmore, everyone infers design. That is, no one entertains the wind and erosion hypothesis when they see these faces on the side of this mountain. But why? Why do we immediately infer design? Is it a probability issue? Well, it just seems really improbable. Well, the problem is that the pile of rocks at the bottom of the faces is also an improbable structure. It'd be very difficult to reconstruct. The rock structure next to the faces is improbable. It probably isn't the exact structure anywhere else in the universe. Well, there's something else going on, Dembski argues. Yes, the structure is improbable or complex, but it's also specified, which means that it adheres to an independently given pattern. It conforms tightly to an independently given pattern. In this case, it's the pattern of the structure of the human face. It conforms very tightly not only to the general features of the human face, but to the faces of 4 U.S. presidents. It's tightly specified. Dembski argues it's the combination of specification on the one hand and improbability or complexity on the other that allows us to infer design. And now the problem with using Dembski's argument for our argument is that Dembski reconstructed his argument as a way of how we infer design within the natural world. We contrast the objects within the natural world with natural law and chance processes. Well, what if you're wanting to infer design in the natural world as a whole? Well, you have to do some different things with Dembski's argument, but we think we're able to do that fairly easily. It's a little more complicated than this, but what the improbability does for us here is that habitable planets stand out in relief against the background of the much more likely places in the universe. It's exceptional. When you see these documentaries in which you see Earth, it stands out. The things we know about what a habitable planet needs stands out against the background. That's the role of improbability here. Okay, most of the places in the universe are quite different from the Earth. And it turns out, if you think of all the things you need for discovering lots of different kinds of things, most places in the universe are going to stand out in their capacity for allowing observers there, if observers could be there for making scientific discoveries. But the more important point of the argument is that we think this is a meaningful pattern. Dembski leaves specification at a highly formal level, an independent pattern. Well, most specifications, in most cases when we infer design, are also meaningful patterns. They're patterns that an intelligent agent would have some reason to bring about. It's a pattern that has value. Well, it's clear that habitable planets have an intrinsic value. They have an intrinsic interest. They're the sorts of things that an intelligent agent might have some reason to bring about. Moreover, the correlation between habitability and measurability is a meaningful pattern. And we recognize that intuitively. Let me give you just a really quick illustration, then we'll take some questions. Imagine you won one of these publishers' clearinghouse sweepstakes, and you get a trip to Hawaii, and you're imagining these wonderful green, lush forests. And as it turns out, they send you to a Motel 6 on the large island of Hawaii and give you $50 and say, have fun. Well, you decide, I'm going to make the most of this trip, so you give $50 to a taxi cab driver, and you say, take me to the tallest mountain on the island. It takes you to Mauna Kea, and you've got your backpack and your Nalgene bottles, and you spend a couple of days climbing up the backside. Just as you reach the top, and you're about to glory in God's beautiful creation, you see a parking lot and some structures, as you see on this slide. You see the famous Keck telescopes. Now you're going to maybe be depressed because I didn't know this was going to be up here. I thought this was going to be by myself in the wilderness. But you wouldn't spend a lot of time wondering why they put telescopes at the top of this mountain, would you? And you wouldn't say, gosh, why didn't they put it in Honolulu, someplace? What's it doing up here? You'd know why it was there, and it's because if you're going to do things intelligently, you're going to put these observing instruments in the best place you could find for observing. That's the pattern. That's the specification that we think is meaningful. It's what you would expect on design. Well, that's a very loose way of reconstructing Dembski's argument to show how you would apply it here, but let me give you one other way of making the argument. And this is in terms of what's called likelihood analysis, or simply the comparison of hypotheses. Think of it this way. If the universe were designed for discovery, the correlation is what we would expect. It would resolve our sense of surprise to discover that those places where there are observers are the best overall places for observing. If the universe is not designed for discovery, it would not resolve our sense of surprise. So the first hypothesis is confirmed. It is more likely than the second hypothesis. And so we think with the suite of different examples of this correlation in the universe and a number of different ways of reconstructing the argument, that a modest conclusion is called for, and it's something like this. The universe is fine-tuned so that environments habitable to observers will provide the best overall conditions for observation and scientific discovery, or to put it more briefly, the universe is designed for discovery. That's our argument. Thank you for your time, and why don't we take some questions? And Hugh's going to moderate.
Okay, we'll try to repeat the questions for you, but before we get into questions, I think it's fair to give Jay and Guillermo an opportunity, because many of us couldn't help but notice that we got Kyler Kuhn speaking across the street here from us. Have the two of you had a chance to talk to Kyler, and do you have any comments on what he's been saying across the street here?
Well, Kyler is a friend, and I know we're irritated that we're speaking at the same time. He's an astronomer at UC Irvine. And Guillermo and I spoke last summer at the American Scientific Affiliation Conference, and because this was a controversial subject, of course, when design people talk about stuff, there always has to be balance for them, you know. And so they said, well, you got to give us a critical response. And we said, well, the book's not out. You have to find a critic. And so we asked Kyler, who had been sort of helping us, to read and to write a critical response, and he did that. I ended up not going. I got a detached retina, and Guillermo had to do it by himself. He was very depressed. But Kyler did the presentation, and then he put it on the internet, and it's the third thing that comes up in a Google search now. And you type in privileged planet. It's called A Critique of the Privileged Planet Hypothesis. Well, we have a chapter 16 in the book, which is called the Skeptical Rejoinder, in which we try to respond to every strong skeptical question that we could think of in 3 years against our argument. It's difficult to go through those in a lecture like this, but we don't think most of Kyler's arguments. One was that it seems to be based on law, and Dembski requires law to be contrasted with design. And of course, we had reconstructed Dembski, and so we actually talked to him yesterday, and Kyler said, "Well, I'm reading the book now, and you know, yeah, it's harder for these arguments now to be made that I'd made before." And so I'm going to ask him afterwards if he'll put that on the website, so it comes up on Google. So, and he did anticipate also some of the arguments. And smart people, every time we've given this talk, have come up with some of the arguments that we have to discuss in the Skeptical Rejoinder chapter. So,
terrific. Okay, anyone? Lady in the back.
Yeah. So the question is the Drake equation, and how does that fit into our argument, and the factors for habitability. And is it still holding up in the SETI community? The Drake equation was developed by Frank Drake around 1960, 1961 to estimate the probability of other radio transmitting civilizations in the galaxy. The problem with the original Drake equation is that it had just a few factors, 7 factors, and 2 or 3 were biological and sociological, really hard to pin down any sort of number on them. We actually present an appendix in our book where we present an updated version of the Drake equation with 20 factors. And now we didn't put specific probabilities on each of those factors, but we gave very generous upper limits to them. And Jay said a little bit about that, 10% each, even being extremely generous like this. There's a less than 1 probability of less than 1 that there'll be any other civilization, even in our galaxy. Okay, and that's where the SETI research is focused, is searching for other civilizations in the Milky Way galaxy, because it's widely recognized that intergalactic travel is pretty much impossible. Okay, the nearest large galaxy to ours is the Andromeda galaxy at 2.2 million light years away. So SETI is concerned specifically with the probability of other civilizations in the Milky Way galaxy. Okay, and so we have an appendix addressing that, and we're both convinced that we're alone in the Milky Way galaxy.
Okay, this lady.
I'm not sure that I have the right name for the moon, but I think it's Europa. Astronomers think there might be liquid water under its icy surface.
Yes.
Does anyone know how much carbon could be on that moon? Like, what would make it impossible for life?
Yeah. So the question is Europa, that probably has liquid water ocean underneath its surface. It's the second Galilean moon out from Jupiter in the Jupiter system. We actually discussed this briefly in our book. We have a section where we compare other planets and moons in the solar system that have been proposed to host life. And we're skeptical of Europa hosting life for several reasons. First of all, sunlight's not available as an energy source. And sunlight is really what drives the biosphere on Earth. Now, people have pointed to deep-sea thermal vents on Earth as independent communities of life. First of all, they're only along for the ride. They generate about 1/100,000th of the biological productivity that, compared to surface life on Earth. So they're really insignificant. And they're not really independent of the rest of life on Earth. Most of those creatures you see on those nature or National Geographic documentaries showing those deep sea thermal vents with those weird creatures and those tube worms, they're all oxygen breathers. All those creatures moving around in there. Where did the oxygen come from? The oxygen came from photosynthesizing organisms on the Earth's surface that were mixed down into the deep parts of the oceans. So when they say that deep sea thermal vents on Earth are an example of a community of creatures that are independent from other life on Earth, that's wrong. Okay, there's very few oxygen sources for the interior ocean of Europa. In fact, Chris Chiba, who works for the SETI Institute, he's a pretty good scientist, specializes in possibility of life in Europa, and he even is skeptical that there's anything there, but he's still holding out the possibility of maybe some very hardy microbes. But you're certainly not going to find dolphins or the lost city of Atlantis. And also the ocean is very deep, so the pressure at the bottom of the ocean where you might have some vents would make it unlikely for organisms to survive because there is a maximum pressure tolerance for organisms. There's a certain range of temperatures and pressures that carbon-based life can tolerate. And so those are just a few of the reasons. There are some other reasons we give in the book also that we're skeptical. But certainly not complex life and still even unlikely for simple life.
Yeah, one other point about Europa is that all origin of life scenarios require a concentration mechanism. And if the ocean is isolated from any drying mechanism, then there's no possibility for the origin of life. And that also applies to steam vents on planet Earth. They're not sites for the origin of life.
Oh, and one more thing. There's no ability to regulate the salt content of the oceans. See, on the Earth's ocean's salt content is regulated because we have continents. And so you have shallow seas where the sea comes in and it evaporates and it deposits salts. There are just vast salt deposits on the continents. Some of you may have seen salt mines, just enormous concentrations. If it wasn't for the continents removing salt from the oceans, most of that salt will be back in the oceans. And the oceans will be too salty for life. But there's no such regulation mechanism for the salt in the oceans of Europa.
Okay, gentleman back there. Yeah.
Oh, no, Robin Collins. No, we can't take questions from you, Robin. It may be too difficult. I'm sorry. Sure.
Design is an important implication, but it also seems to indicate a providential purpose.
Absolutely.
For human civilization. It was built into the universe that we would discover the truths about nature and develop technology. So Michael Denton, for instance, another book refers to the fine-tuning of the universe for the existence of metals.
That's right.
Without metals, we would never have developed the technology we've developed. And so it seems there, with that providential purpose, it has even further implications about our view towards as
That's right.
theists towards science and technology. It's a really optimistic view and seeing that as part of God's providential purpose for human beings. So I think it has much larger actual social and political ramifications.
Yeah.
Can you comment on that?
Now, those are the kinds of questions I like. That's exactly right, and we argue this in the book. Thank you, Robin. It's funny, the trouble that the intelligent design community has caused simply talking about the little rotary motor of one of God's lowliest creatures. Right? It's amazing how much trouble that causes and the implications for that. The implications of our argument are not merely for design, but for purpose. We can often tell that something is designed without knowing the purpose. That black monolith in 2001: A Space Odyssey that the astronauts found on the moon. Nobody really knew what the thing was, but everybody knew it was designed. Stonehenge, what the heck was that for? But we know it's designed. But sometimes you can tell that something's not only designed, but it's designed for a purpose. And that is the implication of our argument, that one of the purposes of the universe is for us to extend ourselves beyond our small and parochial home, to discover the universe at large. And this provides, I think, a robust and optimistic view of human technology, which is an extension of human beings. It extends our view. Now, I think that needs to be properly constrained. It's not some sort of wild, technology can solve all our problems, but it's an optimistic view of technology and of the things that civilization needs, so that we see this as itself part of the design of nature. It's not, human technology and our invention is not some extrinsic thing that is imposed upon nature and is somehow extrinsic and hostile to it, but is in fact a part of the providential ordering of nature. And this is very congenial, obviously, to the Judeo-Christian idea that the natural world is a revelation of God. It's a book that was meant to be read. And in fact, I think that book is disclosing itself here at the beginning of the 21st century in ways that were unimagined and that previous generations knew nothing of. And I think we're just at the beginning. Thank you, Robin.
Okay, this gentleman.
So, can you start again? I didn't hear it. I don't know. Yeah, the question about Peter Ward's position about the origin of life, whether it came via extremophiles. Now, I don't know what particular origin of life theory he prefers, but he is a naturalist, for those of you who don't know. And so Peter Ward and Don Brownlee together argue that simple life is probably common in the universe because it's only a matter of getting the right conditions together at the same time. Liquid water, the right chemical ingredients, etc. They recognize that the constraints imposed by the laws of physics are very severe. Okay, only certain places will have those, but it's only a matter of getting liquid water and the chemical ingredients together, and then life will automatically be generated. And so they have the view that simple life will be common in the universe, and they're a bit skeptical, though, about some of the claims made about extremophiles. For those of you who don't know, extremophiles are various types of microorganisms that are found to live in extreme conditions, extreme temperature, extreme salinity, extreme pressure, extreme dryness, etc. And therefore, because these can live under extreme conditions, therefore we can find them in just about any other place. Maybe Europa, maybe the surface of Mars. Well, we argue in the book against this by saying that life on Earth is very interdependent. And there's a lot, the biosphere has to be very active in order to make the Earth habitable enough to remain habitable for complex life. The microorganisms, the phytoplankton in the oceans and the trees and everything actually reinforce the temperature stabilization mechanisms of the Earth, the carbon dioxide feedback cycle, for example. And it's because of the strong activity of the mesophiles, which I think Q mentioned, or Fuzz very briefly, that we can have the extremophiles hanging on. They're free riders, basically. Okay. So we do address that very briefly in our book. But again, I don't know specifically what Peter Ward's favorite origin of life theory is at the moment.
Yeah, and for those of you who are interested in the latest issue of Astrobiology, the lead paper is Extremophiles, Why They're Irrelevant to the Origin of Life. You really can't originate extremophiles, and there's a great article on that. Yes?
We address variations in the solar output and how it affects the climate. And so, for example, we present evidence that's obtained from various paleoclimate records, like ice cores, marine sediments, and such things. And there have been strong correlations found between the variations in the climate and inferred variations in the solar output through various proxies, especially beryllium-10 and carbon-14. Which the production of which is affected by the sunspot cycle. And we can actually reconstruct the solar variation going back tens of thousands of years. And it's found that the climate actually does correlate with the solar output very well. And it's and I consider this to be still unproven, it's kind of speculative, is that one of the reasons for the stability since 12,000 years ago of our climate on Earth is because the sun has been unusually stable during these 12,000 years. That's not been proven, but that's one of the explanations that's being debated, and I think it's a very reasonable one and a possible one, that in fact most of our stability derives in our climate today is the result of the sun being unusually stable these last 12,000 years. But there are other factors that come in because the Earth's orbit shape changes during that time. The tilt of its axis changes very little, but it does have an effect on the climate, which is another interesting thing. We found through paleoclimate records that the Earth's climate is very sensitive to small changes in the shape of the Earth's orbit or the change of its tilt, which confirms that this is something you need to fine-tune considerably, is the stability of the shape of the Earth's orbit and the tilt of its axis.
Go ahead.
In my own internal struggles and trying to think through how to communicate to my scientific colleagues that maybe had doubts that I had earlier. And one of the discriminating issues was that we could all kind of agree on as the evidence that the universe gives of God's design, which are so beautifully presented in these last couple of days. But one thing that you guys have all touched on, and certainly you touched on explicitly in saying tuning equals Christ as Savior plus or minus a small error. But I think taking it one step further in that these kinds of arguments, I think, are discriminating arguments between other monotheistic religions, because this presents a loving God who was this really solid inference of a loving God who was really extravagant with us. And certainly we see on the personal side that the Bible exhibits that, and the Quran does not.
Right.
And even Judaism
Right.
does not.
Well, if you want to see a specific treatment of that, the latest edition of our DVD, Journey Toward Creation, has a 30-minute clip at the end of the journey from planet Earth to the edge of the universe, where we critique what you see in the documentary with Judaism, Islam, Hinduism, Buddhism, animism, Mormonism, Christianity. So we actually go through the different religions of the world and say, how does that comport with all this design evidence that we see as we take this journey throughout the universe? So you'll see that at our table at the outside here. Yeah, Dwayne.
I think you've done a beautiful job of illustrating these many very spatial conditions that do exist, and therefore gives evidence God has prepared this universe for it. Now the question is, how did this all come about? All these spatial conditions. Apparently you accept some version of the Big Bang theory, which of course is the same theory the atheists suggested, and so he said we agree with that. Now you believe then these natural laws and natural processes were there operating from the very beginning from the hydrogen aspect of the universe at the time. Isn't that so? And these natural laws are still operating today as they operated then.
Yeah.
However, the natural laws and natural processes which now govern the universe are causing its inevitable death and destruction. Now what is the atheist going to say? Did God build that in there? Did he build in this natural law, the second law of thermodynamics, which is causing the inevitable death and destruction? And if so, if this law must have been operating from the beginning, the natural laws and natural processes which now govern the universe are causing its death and destruction. How could they be responsible for its origin? How are you going to answer to the atheist then in that case?
Okay. Let me clarify that we started completely with naturalistic assumptions and with mainstream science. We granted them. Okay, so we say, grant that the universe started in the Big Bang, and we don't say what caused the Big Bang, we just say it started with a Big Bang. Personally, we're theists, and we do have a belief that God created the universe, and the Big Bang is evidence of that. But granted that natural processes have operated throughout the universe, we've taken mainstream science, the sciences that are most strongly supported by the evidence today. Where does that take us? And we claim that actually points towards evidence of design. Okay. Now, the bigger question of, well, you have these same laws that cause the universe to reach a certain point from hydrogen or a quark gluon plasma, to be more precise, to the present time, will eventually result in the annihilation of the universe, because eventually everything will expand so quickly that stars will cease to form and we'll all die, or at least there'll be a future limit to the lifetime of any complex beings. Then you're getting into a question of what did the Creator intend in these other areas, and that, I think, is somewhat generally related to the problem of evil. Okay, why is there evil? Why will the universe eventually cease to function? I think are somewhat related questions, and we're not going to address those. Okay, those are questions that are specific to what the other intents the Creator may have had. Okay, we just ask the very specific question about habitability and measurability, and we keep focused on that particular aspect throughout the book.
Okay, and Dwayne, reasons to believe we do address the issues that you raised. First of all, the Big Bang is opposed by the atheists. It's not supported by the atheists. They see it as a Christian model, as I mentioned yesterday. And then in terms of the death that you're referring to specifically, the point we're all making here is that God creates the universe for human beings with the intent that we'd be able to have civilization and high technology for the fulfillment of the Great Commission. And this requires resources. And so what we see in the crust of the earth are the resources that have been accumulated through hundreds of millions of generations of life and death, and we're the beneficiaries of that. So in that sense, I don't see this as something that is bad, but rather it's something that's a sign of God's blessing upon humanity, that He gave us coal, oil, natural gas, limestone, the ingredients for cement, and for that matter, all the concentrated metal ores we see in the face of the earth are there thanks to millions of generations of sulfate-reducing bacteria. So this is all evidence of God's beneficence towards the human species.
Sure. Excuse me.
Anyway, at any point, just one, you don't have a natural theory. You don't have a theory that can be tested naturally. You don't have that. If God had to do anything, one little thing, you've destroyed your natural explanation.
Right, and yeah, that's right. There's a lot of issues here, and I mean, we understand. Eugene Scott says you can't put God in a test tube. You also can't put a star. You can't put gravity. You can't put a lot of things in a test tube. And we see many things we infer from their effects. And so I think this is the whole point of the design argument, the design inference, is that there are empirically detectable markers for the activity of an intelligent agent that can be tractable empirically, even though you can't put any agent under a microscope. And so I think divine agency, at least in principle, I mean, if God created the world, he could presumably leave his fingerprints all over the evidence. Right. The other thing about our argument is that we're saying, granting the laws of physics and stochastic processes, could you still infer design? But we're not begging the question. It's certainly possible that Newton was right, that God directly set up the orbits of the planets. Any theist has to grant that's maybe how God did it. What we want to do is sort of called a minimal facts argument, in which you argue if you can get to a conclusion in as few premises as possible, that's a good thing. The best argument would be one that gets from the law of non-contradiction to the doctrine of the Trinity. Now, I can't find one of those, all right? But if you can get from minimal facts to the implication that the universe is designed for discovery for observers like ourselves without resolving the completely legitimate but complicated theological questions about evil, then I think that's a good thing.
Okay, with that, we are going to have to allow you to get to the next session. We're about 2 minutes over. We will be around for a few minutes afterwards if you got private questions, but thank you.
I don't really need to offer much of an introduction to our guest. He is a professor of law for 30 years at UC Berkeley, author of a book that helped to catapult us to where we are today, Darwin on Trial. Philip Johnson, thank you for coming to greet us this morning.
Good morning, friends. It's so exciting to see you all here. Let's take a moment this morning and imagine one of those apocryphal gospels that are so much in vogue today. And in this one, Satan takes Jesus in the wilderness up to the top of a mountain and displays to him all of the great institutions of research. And he says to Jesus, all of this research money belongs to me, and I will convey it to you. If you will simply agree to let me set the questions to be answered and the intellectual agenda for answering them. Bow down to me, accept these terms, and all of this wealth shall be yours. Jesus said, man does not live by research funds alone, but by every resource and talent that God conveys to us. Looking over the program for this morning and just the first page of it that I have for me, I see how this schedule indicates some of the breadth of interests and topics which the intelligent design movement is addressing. Much of our program yesterday, all of our program yesterday, I suppose, was about natural science. And sometimes people outside and inside the movement get the impression that this is just an assertion of a particular kind of position in biology or cosmology. This is a science movement. Well, certainly, scientific research is an important aspect of the movement, as it should be, and I honor that. But I would not be happy if the intelligent design movement and its people became totally dedicated to the practice of natural science as if it were the only method of learning and knowing and making intellectual gains. In fact, that philosophy that science is all there is one of the things that we strive to counter. If you want to get a picture of the breadth of the movement, the differing topics it addresses in science and outside of science as well, that by the way, being a very murky border, what is in and what is outside of science is not really very precisely definable in principle. But you might want to pick up the collection, Darwinism, Design, and Public Education, which covers such a variety of topics and variety of authors in their different styles. Now, one of the co-editors of that volume is John Angus Campbell, a professor of rhetoric at the University of Memphis, who will be here with our friend Michael Keyes from Oklahoma Baptist University to talk about philosophies of education, ways of teaching the controversy, and the preparation of teaching materials. I think if there's one question I get asked more often than any other, it is what teaching materials are available. See, this is like a scientific research program. You have a general principle, like teach the controversy, open up the fundamental assumptions, but then you need the engineers to come in and turn it into something real that can be used in the classroom, in public policy. And also that question of teaching materials is one that is very much on our agenda. So that's part of this morning's program. And then going on, we see a program on Darwinism and its impact in public policy, the case of Germany and America. Learning just how much those two countries had in common in the first half of the 20th century and how much they owed to Darwinism in the founding principles of their intellectual, political, and legal life is pretty shattering, pretty frightening. I'm also particularly glad to see this topic with Richard Weikert's wonderful book on From Darwin to Hitler, the impact of Darwinism in German intellectual life. And I'm glad to see this not only because of the specific topic, but because it is an illustration of another dimension, another field of study in our grasp here, intellectual history. Sometimes I say that if there's one academic field more than any other to which we could fit our work, it might be intellectual history. See, that's what, in fact, I think that one of the great accomplishments that we will eventually have is that Darwinism itself will be taught in courses on British intellectual history. That is the proper fit for that topic. And how Darwinism was replaced by better thinking will be the modern, the last week of perhaps of the course. Then we have Philosophy and Intelligent Design in the Myers Auditorium with Nancy Piercy, an important member of what I sometimes refer to as our second wedge, the cultural and literary wedge, to complement the scientific wedge, and one which deals with the basic questions of worldview, the assumptions that people make. The great philosopher Alfred North Whitehead once wrote that if you want to know what is important in the thinking of any age, don't look at the things that the people are debating. Those are not the most important things, because the fact that they're being debated indicates that they're somewhat in doubt. See, we're moving Darwinism to be one of those things that's being debated. But the most important ideas are the ones which are implicit throughout that culture rather than explicit. The things that everybody takes for granted because we now know today, and everybody knows. And everybody knows a lot of things that aren't so, and a great part of our work is pointing out some of those things that everybody knows that aren't so. That is a tremendously important part of the intelligent design work. Then we see on the literary side, Jonathan Witt, a very gifted writer who works with our Discovery Institute. And that's part of the engineering, you might say, as well. There are ideas, and the ideas have to be written up properly and expressed properly. And Jonathan is certainly one who not only has the ideas, but helps others to express themselves. And we have here with us, I see in the front row, Denise O'Leary, a Canadian journalist who has been helping to teach us that if we're getting a bad press, as we often are, the thing to do is not to whine about it. I detest whining. But to say, what can we do about it? And one of the things that we can do is to train ourselves to speak and relate in a way that journalists are able to hear and understand what we are saying. See, this is the educational project, just like we have to speak in a way that, and write in a way that our intended audience, whatever it is, it might be high school students, can grasp and understand what we're saying. A whole part of my own work has been trying to write in a way that that people in the university world can understand what is being said and can help to realize that they are not the independent, inquiring, courageous minds that they think they are, but are in fact probably just following fashion. Chapter 1 of The Wedge of Truth, which is almost semi-autobiographical, tells you how that comes about. People think that they are thinking for themselves, but in fact they have just followed the fashion, as I did when I was a young man. So we want to help people to learn to understand that, to understand how they can free themselves of the tyranny of fashion and the tyranny of those implicit assumptions that govern the thinking in the matters which are explicit, and that's something else that I have been trying to do. And you see that I see even on the program, besides some of the people that I've mentioned, I want to make particular mention of Roger DeHart, a high school teacher who has suffered the oppression and persecution that comes from trying to bring up some true scientific things that are embarrassing to Darwinism. And it doesn't matter, those may be articles that are in Nature, that were written by Stephen Jay Gould, that were have a completely satisfactory scientific pedigree, but if they tend to suggest problems in Darwinism and materialism, then it's illegal, thinks the sadly misnamed American Civil Liberties Union. The America that badly needs to examine its conscience and methods, then they may join the oppressors, because this is the sacred holy of holies of the materialist modernist mindset, and we have to help people to understand that their thinking is in a prison, not free as they think it is. And sometimes, Denise O'Leary has told us that actually some journalists want to know that when it's so, and will listen if they're given a chance to see it by the way that we express. So that is just a very brief overview of some of the things that are happening today. There's more science too, and that's I'm sure very good, but I'm not giving so much mention to it because you're aware of a lot of that already, and that also will be in that book, Darwinism, Design in Public Education. Some of the best scientific articles are there, and as well as from the related areas of endeavor that we're involved in. So I'm thanking you all for being here. I have met people. I'm particularly thrilled by some of the unexpected people I meet. The carpenter who has come all the way from Indiana to be here and to soak in this atmosphere and to follow up his thoughts, and but that's just one of many people that are taking their own time, their own expense to come and participate in something that's outside of their normal everyday Monday to Friday line of thing, because they're thrilled by what's going on. And the only thought that I have, when I see the excitement here, when I see the people coming, when I see the size of our gatherings and the enthusiasm, like, what is wrong with the rest of the world? Why don't they catch some of this excitement? Well, that too is our job. Not to complain about that situation, but to do something about it. And when people ask me, what can I do if I'm not a professional of this or a professional of that? If you can help a few other people to understand these issues and to catch the excitement of it, to see that something is really going on, you've done a world of good. Amen. If you get to 10 people, that can become 100 awfully quickly. And so that, I think, is all that you have to do to contribute an enormous amount. Get people to watch a video, to talk about it, to begin to get the basis of what's going on, not the details, but the fundamental thrill. Well, I'm sure that the events of today will help us all to see what's going on and to feel the excitement. And they're awfully varied set of events, and so enjoy the buffet. Thanks for coming.